Before we begin, I should mention this video is aimed at people who have a decent level of coding experience. Alright, the first thing we do is create our main class. We create the main function, which is the start of the program. Now, we need to decide how we are going to input the iris data. There's many different ways you can do this. You can read in from a text file or make a select call to a database. But for simplicity, I'm going to hard code the data in. We will store the iris data in a 2D vector of doubles. Make sure to include the vector header, and I'm going to use the vector namespace to make the code easier to read. If we copy the data directly from the dataset, all of the iris setosa text will need to be changed to 0 to represent the class, and iris versicolor to 1. Skipping ahead to save time, you can see all of the setosa data instances have a 0 at the end, and all of the versicolors have a 1. I put all of the setosa data first, which, if you remember from the concept video, ordering by class like this is really bad. We need to make sure we call shuffle before we start training. We also need a set of weights, which will just be a vector of doubles. We can initialize it to a size of 5 because there are 4 attributes plus the bias. Now that we have our data into our program, we need to build the perceptron. We'll create a new source file and header file. What does our perceptron need to do? First, we can set the constant variables, the bias input value of 1, and the max number of epochs to stop at if it's not capable of finding a perfect solution. Now we can go ahead and set up all of the functions our perceptron will need. First, it needs the integration function, which performs the dot product, so it will take in one input vector and the weight vector. Both can be constant since they're not being changed. Now we need our activation function, which takes in a single value and outputs 1 or 0. Next, we'll make two functions, one to train the perceptron and one to use it after training is finished. The training function will take the 2D vector of all inputs and the weight vector. Since we'll be changing the weights and shuffling the input order, they can't be constant here. The classify function will take in one input vector and the weight vector, and it will output 1 or 0. Lastly, we need a function that will randomize the weights for us initially before training. Okay, now let's build these functions. We'll include our header file and vector because we know we'll be using those. First, we'll build the integration function. All this does is take the dot product of the input and the weight vectors. If you want to do this manually, it can easily be done with a for loop like this. And remember, we want to use input.size -1 because the final index stores our class variable, which is not used in the dot product. During each loop, it multiplies the input and weight value at the index I and adds it to the sum. C++, however, has a built-in function for this called the inner product, which is defined in a numeric header, so let's use that. inner product takes 4 parameters: the beginning of the first set of numbers, the end of the first set, the beginning of the second set, and the initial value of the sum of the products, which we want to be 0. Next, we build the activation function, which is very simple. An if-else statement which determines if the input is greater than or equal to 0 or less than 0. The randomize weights function is a little tricky in C++. You could just pick random values manually, but that gets tedious when you have a lot of weights. We'll use the random library to do it automatically. Random device gets a random integer value, which we will use as a seed. Default random engine is an object that generates uniformly distributed numbers, which will be the same every time without a random seed. Uniform real distribution is an object that transforms the sequences of numbers generated by our default random engine into values between -0.5 and 0.5. Now we can use a for loop to change the value of each weight to a random number. Now to build the training function. First, we make a for loop for the epochs. One loop of this should go through the entire 2D vector of training data. Then we make another for loop to calculate and train each data instance, just like what I showed in the concept video. Remember, we also need to shuffle the data at the beginning of each epoch. This can be done with the shuffle function, which takes the beginning of the vector to be shuffled, the end, and the seed used to determine the order. For each calculation of a data instance, we first call the integration function, which takes in one vector of training data, which we can get by using the index we are currently on, j, and our weight vector. Then we add our bias to that value by getting our static value of 1 and multiplying that by the last index of our weight vector, which stores the bias weight. And finally, we call the activation function, which returns the calculated output, or the class our perceptron classified the data as, 1 or 0. We then find the error based on the answer we provided minus what the perceptron found. And remember, the input we provide is in the last index of the input vector. If the error is not 0, we train the perceptron. A simple for loop will add the input times the error to each weight at the same index. We do not train the bias weight in the same for loop because we need to use the static value of 1, not the last index of the input vector, which is the class variable. Now we can train the bias after the for loop. At the end of each epoch, we need to check if the perceptron has achieved perfect classification, because if it has, we can end the training altogether. After all, if the perceptron is correctly classifying all of the training data, no training will happen. We can do this by keeping track of a counter. Every time the perceptron is incorrectly classifying, we can increment the counter. And at the end of each epoch, if the counter is 0, then we can go ahead and break out of the loop. The classify function is similar to the train function, we just leave out all of the training parts. And we change the input vector to just itself, a singular vector. We also want to return the output of the activation function, as this is the classification. Now, back in the main function, we can include our perceptron header file and make a call to randomize the weights. Then we can call the training function. Let's also add some output so we can see what's going on. We can include the IOStream header and print the weights before and after. We can use a ranged-based for loop to easily print out every value in our weight vector. And let's also print out the number of incorrect classifications after each epoch in the perceptron. And we will also need to include the IOStream header file in our perceptron source file. Now we can run it and see what happens. Here you can see the weights before and after training. And we can see it was able to correctly train itself after only one epoch. Here's another thing to point out. You will notice the final weight values after training are different every time. This is normal and to be expected because we are randomizing the initial values of the weights and also randomizing the order of the input data. In statistics, we learned that when training a neural network or perceptron, it's recommended to set aside about 10% of the data to test how accurate it is after training. We'll do this at runtime, so the 10% of data taken is randomized each time. Let's create a new 2D vector to store these data instances. We can use a for loop to add the last value of our dataset to our test vector with the pushback function. And then call popback on the dataset vector to remove it. Now, after we perform training, we can make a for loop and classify each instance of the 10% of data we set aside to see if the perceptron is correct. To do this, we can use a for loop and call the classify function on each instance of data. Then we can compare what the perceptron found to the answer we provided. Don't forget, we need to randomize the order of our data vector so the 10% test data taken is random each time. And here we can see that it does correctly classify these data instances. Alright, now that that's working, let's come up with some new fake measurements and see if the perceptron can classify them correctly. I'll make a new 2D vector and put in two made-up measurements that have values similar to iris setosa, and two that are similar to iris versicolor. We can change the values by a little bit, so it should still be close to real measurements. Now we can make another for loop and classify each one. And with our output, we can see that it does correctly classify. Now I'm going to walk through the training portion of the training function with the debugger to make sure it's working properly and to see exactly what's happening. Let's set a breakpoint for the debugger at the beginning of the for loop that calculates each instance of data and run the code. You can see in the bottom left the variables currently being used. As we step through each line of code, we can see how each variable is changed. If we look at our input vector, we can see the value of each attribute, and our weight vector shows the current value of the weights. First, we step through the integration function, which returns negative 4.8, the dot product. Then we add the bias, which is at the last index, or the fourth index of our weight vector. Then we step through the activation function, which, since the input is negative, should return 0. Now we calculate the error by subtracting the 0 it found from our expected output 1. Since the error is 1, we will perform training. For each loop of training, because the error is 1, we add to the weight at index k the input at index k. And here we have 5.59 added to negative 0.4, which becomes 5.19, as expected. We can watch it loop through every weight and see that it's working correctly. Lastly, we check to see if the bias is being trained correctly. We have the error value of 1, which should be added to negative 0.2. Correct. Stepping through again and again, we can see exactly how the perceptron is working. Lastly, I would like to showcase the usefulness of the bias. I've created a new dataset with 2 attributes so it can be easily visualized. There are 2 classes here, one with larger values and one with smaller values. However, they are all scattered in the positive x and y direction. This is just like the problem shown in the concept video. Let's comment out the bias calculation in our perceptron and see if it can correctly classify the dataset. As you can see, it was not able to classify them. We can even up the number of epochs to 10,000 and see if it can find a solution. Nope. Now let's turn the bias calculation back on and see what happens. This time, it classifies correctly after only 2 epochs. If you would like to turn this into a real application, one way to do it would be to save the value of the weights after they have been trained, and instead of randomizing the weights and training it, simply set the weights to those values initially. Then you can make a text prompt to input the 4 measurements by using getLine and the string library in a while loop that repeats indefinitely. And all we are doing is prompting the user for input for each of the 4 attributes, then setting the value of the input vector to the value the user just entered. Then you can just call the classify function, which tells the user which flower type they have. If we input the first iris setosa data instance, it tells us what it is. The same works for the first instance of iris versicolor. If we input some random numbers, which are clearly not iris flower measurements, it will still classify based on the weights. You can then build the project and use the executable whenever you need to classify an iris setosa or versicolor flower. And that's all for the video. I hope this helps in understanding the perceptron because I know when I first studied this in college I was completely lost. The code is on GitHub, a link is in the description. If you have any questions or notice any mistakes, feel free to comment and I will do my best to help.